Hey everybody, Dr. A here, and in this video we're going to be exploring an example of static friction, and we're going to be referencing the Hibbler Statics textbook. So before we dive into it, go ahead and hit like and subscribe and be on the lookout for other content like this. All right, let's get started.
That has a 20 kilogram mass that has an 80 Newton force applied on the left side here at an angle of 30 degrees from a horizontal axis and at a height of 0.2 meters above the surface that the box is sitting on. If the coefficient of static friction is 0.3, we're being asked to determine if the box remains in equilibrium. And remember, this coefficient of static friction is developed between the bottom surface of the box and the actual surface it's sitting on, okay? We're also given a width of the box of 0.8 meters. So let's go ahead and state under the solution. The first thing we're going to do is draw a free body diagram of this system. So I'm going to go ahead and draw our box here. And the first thing we want to go ahead and get is the weight of the box. So the weight of this rectangular box is going to act right at the centroid of the box, which is going to be at a 0.4 meter dimension in the horizontal direction. And that weight is going to be equal to what? It's not 20 kilograms because the 20 kilograms is its mass. It's 20 times 9.81, which will be 196.2 newtons. And again, this is going to be acting at a distance of 0.4 and 0.4 meters because a weight is always acting through the center of gravity of the box, which for a rectangle is right in the middle, okay? So the next thing we're going to draw on our free body diagram is our applied force, which is right here, and that's 80 newtons. And that's acting at a 30-degree angle and a height of 0.2 meters. This definitely does not look to scale, but that's okay. The next thing we're going to draw on here are the two forces that develop at the surface, the bottom surface of the box. So the first force that develops is going to be a normal force, okay? And then the second force that's going to develop is a friction force, okay? So we're going to call that F. We're just going to call that F. How about we just call it F for now? We'll reserve F sub S for something else in a minute. So we're going to call that friction force F and normal force N. Now remember, as discussed in our previous video, there is going to be a slight difference in location between the normal force and the weight. And so if we kind of project some lines here, then this dimension right here, we're going to call dimension X like this, okay? Now, the next thing we want to do is establish some kind of origin. Now, your origin or reference point could be anywhere on the box. One of the corners, one of the bottom corners would be a good spot. I'm actually going to pick the center bottom as my origin. And I'm just going to call that point O. And the reason I'm picking that point arbitrarily is because my weight is acting through the center of the box, right? So if I sum moments here later in this problem, I can eliminate the moment generated by the weight of the box because it'll pass through that origin. But again, you could just as easily put your origin at this left most corner, left bottom corner. You would just have to sum moments and include the weight of the box in there, okay? So let's take a look here. What all do we have and what all do we need? Well, we have three unknowns, okay? There are three unknowns. What are they? Well, N, the normal force, the friction force developed, F, and what else? Do you see anything else here we don't know? The distance X that our normal force is away from the line of action of the weight of the box, which is also the same distance X it is away from the origin, okay? So we have three unknowns. What can we apply? We can apply three equilibrium equations because what is this? This is a two-dimensional rigid body, right? All this is a two-dimensional rigid body. So here we go. We're going to say sum of the forces in the x direction equals 0, and everything in the x direction is going to come into play here. So we're going to have 80 newtons times the cosine of 30 degrees, and then we're going to have minus that friction force F equals 0. Okay, now you may be wondering, why did I point the friction force to the left? Well, again, the friction force F is an unknown, so you really could point it to the right if you wanted to. But remember, a friction force develops acting in the opposite direction of where something will tend to move. So if you look at how this 80 kilonewtons is applied, this box is going to want to move to the right. So it makes sense that the friction force would develop and point to the left. But we'll see. We'll calculate this and see what happens. Let's do some rearranging. We'll get the friction force equals 69.3 newtons, and it comes out positive, right? So it is, in fact, pointing in the direction we assumed, which is to the left, okay? So that's one of our unknowns. We can check that off if you want to. Now what we can do is say sum of the forces in the y direction equals 0. We take up as positive. And when we sum forces in the y direction, we're going to have minus 80 newtons times the sine of 30 degrees. And we're going to have minus the weight, so minus 196.2 newtons. And then we're going to have plus the normal force N equals 0. And that's all. That's everything in the vertical direction. So we can do some rearranging, solve for the normal force, and we should end up getting a positive 236.2 newtons. So the positive indicates that this normal force is in fact pointing up, which is the direction we assumed. Now the last piece that we need is this unknown distance x. So I can apply my moment equilibrium equation to solve for that. So I'm going to say sum of the moments about that origin O taking counterclockwise positive equals 0. And again, remember, we could have put this origin anywhere, and that would be okay. We could put it anywhere we want, but it's convenient to put an origin somewhere where you can eliminate one of your terms in an equation, okay? So here we go. When we sum moments about point O, what all is going to come into play? Well, definitely the each component of the 80 kilonewtons, right? We're going to have to resolve that 80 kilonewtons into a vertical component and a horizontal component, and each of these components is going to have its own perpendicular distance away from the origin right here, okay? So let's do this one at a time. Let's look at the vertical component of the 80 kilonewtons. I'm going to say 80 kilonewtons times the sine of 30 degrees times its perpendicular distance to the origin, which is going to be 0.4 meters, okay? And that's tending to cause a counterclockwise tendency of rotation, all right? So that's positive. What about the horizontal component? So the horizontal component is here. That's tending to cause a clockwise tendency of rotation. So we're going to say minus 80, I've been saying kilonewtons, haven't I? It should be newtons. 80 newtons, my bad. We're going to say minus 80 newtons times cosine 30 degrees times 0.2 meters, right? Its perpendicular distance is this 0.2 meters. And we're done with the 80 now. The weight of the box does not come into play here because that's acting at the origin. What about the normal force? Yeah, absolutely. That's going to cause a moment about O. So we're going to say plus that normal force times X. And what about the friction force? Friction force does not come into play because it's acting through that point, right? So we're going to say equals 0. And remember, we know the normal force, right? We already calculated that. That's the 236.2 newtons. So we can substitute that in, and I'm going to make a note here. I'm going to say that we substitute that into this value here, and we'll do some rearranging, and we can solve for X, and we will get a value of negative 0.00908 meters. If you wanted to express that in millimeters, that would be negative 9.08 millimeters. Now, what does the negative indicate here? The negative indicates that X is actually on the left side of the origin O, okay? So that means that instead of the normal force developing to the right of the origin, the normal force is actually developing just a little bit to the left of the origin, okay? So remember, we assumed X was measured from the origin going to the right. We got a negative, so X is actually measured from the origin going to the left. So that's what that negative sign means. Now, we're not quite done yet. We solved for a bunch of unknowns, but did we really answer the question yet? The question that the problem asked was to determine if the box remains in equilibrium, all right? So how do we do this? So the first thing we need to do is investigate sliding, okay? So we're going to say, will the box slide, okay? So let's figure that out. What would be the friction force that is the maximum friction force at that surface? Okay, so the max friction force, and this is static friction force, at the surface is what? It's going to be F sub S equals mu sub S times the normal force, which is 0.3 times 236.2 newtons. And so the friction force, the maximum friction force, is going to be 70.9 newtons. And we're going to say, since the developed friction force F is less than F sub S, no sliding will occur. All right, so again, we calculated F a few minutes ago as 69.3 newtons, and that was less than F sub S, which equaled 70.9 newtons. So that's what we mean by that. The friction force F sub S is what the horizontal component of the applied force has to overcome in order for sliding to occur. And it does not overcome this. It's less than the friction force that's resisting the motion. So the box is not sliding, okay? What about overturning? So we're going to say, will the box overturn? So the answer to that is going to be no, okay? The answer to that is going to be no. And we're going to say, since X is less than, since the absolute value of X, is less than 0.4 meters. So how do we know that? Well, where am I kind of coming up with that from? Well, remember, the width of the box was 0.8 meters, okay? And this X right here, sometimes we call this distance an eccentricity. So this eccentricity distance is within the boundaries of half of this box, right? Measured from the origin. Now, if X was calculated and it was larger than 0.4 meters, then the box would end up tipping over or overturning. But since it is not, it is within the half width of the box, it is not going to tip over, okay? You can kind of read more about the potential of overturning again in the sections 8.1 and 8.2 in the text. But that's it. That's the final conclusion. So finally, we're going to say, therefore, the box remains in